sampling distribution of sample statistics, whether the statistic is the means of the samples or the proportions of the samples or the standard deviation of the samples, is the distribution of the means of all of the samples of the same size, or the distribution of the proportions of all of the samples of the same size, and so on. For example, suppose we have a distribution where the population consists of the digits 1, 2, 3, 4, and assume that this has a uniform distribution, meaning there's a quarter chance that 1 occurs, there's a quarter chance that 2 occurs, and so on. Thus, when we graph this distribution, we see that the graph is a flat curve. This is a characteristic of what we call a uniform distribution. The x values are 1, 2, 3, 4. Each has the probability of 1/4, and so on. The density curve is therefore just simply a flat horizontal curve. This random variable has a mean or expected value of 2.5. Whether we take 1 times a quarter plus 2 times a quarter plus 3 times a quarter plus 4 times a quarter to get 2.5, or using the properties of the uniform distribution where the mean is a plus b over 2, where a is the lower bound, 1, and b is the upper bound, 4. 1 plus 4 over 2 is 2.5, precisely the number in the middle as expected from the graph. Suppose now we are interested in the sampling distribution of the mean of simple random sample of size 2. What that means is that each of the sample has size 2, and we're going to construct as many as samples. There are 16 of samples of size 2. We can list them all. For instance, 1, 1, 1, 2, 1, 3, 1, 4. So far, there are 4 samples here. Each sample has the size of 2. We're going to list all 16. Now, we are interested in the sampling distribution of the sample means or the sample average. So we're going to compute the average of each of these samples. What that means is that we will end up with 16 numbers. Each of the number represent the average or the means of each sample. The first sample, 1, 1, has the mean or average of 1 because 1 plus 1 over 2. The next sample has the mean of 1.5, 2, 2.5, 1.5, 2, 2.5, 3, 2, 2.5, 3, 3.5. Again, these are the averages. 2.5, 3, 3.5, 4. These 16 numbers that we circled are the sample means. We now have 16 numbers in front of us. We're going to examine the distribution of these 16 numbers, which is the distribution of the sample means. One way to examine the distribution of these 16 numbers is using the dot plot. The first sample has a mean of 1. The second sample has a mean of 1.2, 2, 2.5, and then 1.5, 2, 2.5, 3, 2, 2.5, 3, 3.5, 2.5, 3, 3.5, 4. We can't help but notice that the distribution of the sample means is roughly a bell-shaped curve, which is a normally distributed distribution, even though the distribution of the values 1, 2, 3, 4, originally it was not a bell-shaped curve. In fact, it is a flat, uniform curve. But the sampling distribution of the sample means is now normal. It looks like it has the mean or the center or the average. So the average of these 16 numbers is still 2.5, which is the same as the mean of the original distribution. This process, where we take repeatedly the samples from the population to compute the sample statistics and examine the distribution of these sample statistics, whether it is the mean, proportion, standard deviation, this is called the sampling distribution. This is very important because what this is saying is that regardless of what the original distribution is, we can obtain a roughly normal distribution, and with the normal distribution, it is easy to work with. We know how the normal distribution behaves. The advantage is that we will end up with working with the normal distribution instead of any other distribution that we don't know, such as the skewed distribution, uniform, or again, it can be any distribution, but the sampling distribution, which is this process similar to what we just did, turns to a normal distribution.